Hello there, thank you for joining me again today. On the bench we've got yet again the wonderful world of microwave and RF engineering devices. We've got today for review some attenuators, and we'll discuss the different types of attenuators, what applications are used in, power ratings, frequency response, accuracy, and we'll look at some pricing as well, what these are normally priced at, but the different types of applications as well, not just attenuation but splitting, power splitting, power splitters, variables as well as fixed attenuation. So we've got quite a range of attenuators here, and a bit of a mixture of manufacturers from Narda, Radial, Marconi, AEI, mini circuits, Andrew. We've got a bit of everything on the bench today to show you. But first of all, I just wanted to show you one of the most expensive attenuators that I've got, that I've acquired. And this is a Narda one. Now, Narda been in the marketplace for many, many years, decades. And of course, there's meteorology grade components, aerospace defence, commercial grade components. This is a meteorology grade component. And this came with a data sheet as well. This is a thumbwheel variable attenuator. Goes up to 69 dB's attenuation, and this is a data sheet for it. Now, before I tell you how expensive this is to purchase, we'll just have a look at the specification. So this is the higher model one. This ends in the 69 part number range, and this is in this column here. But it's got an extremely wide frequency range from basically 0 to 18 gigahertz, so that's quite a wide range, but its accuracy as well is exceptional. And again, this is a type of thing that when you're paying this kind of money that I'm going to tell you this were purchased for in a moment, then you'll be able to understand why. But we've got basically 10 dB range plus or minus 0.5 dB accuracy, but right up to 69 dBs we've got plus or minus 2%. But bearing in mind that's across that frequency range. So for example, the VSWR as well, which is here, this one is rated DC 12.4 gigahertz, 1.5 VSWR, 1 to 1.5 ratio, 12.4 to 18 gigahertz, 1.65. It's a 50 ohm nominal impedance. We've got some other specifications as well on the rear. Again, quite a lot of detail regarding its physical construction, how it's mounted, dimensions, etc. Which, if you're a military component selector or somebody who's looking at doing a particular design or acceptance testing regime in a laboratory, you need to know that information. So it's got these little mounting holes underneath, etc. So that gives us quite a bit of information on the name plate on the top. So it's telling us that it's a step attenuator, its frequency range, model number, attenuation, and how much power it can take, which is obviously a good piece of information. It tells us 2 watt CW, so we know we can use it up to 2 watts. But it's very heavy, very, very well constructed. It's one of the best attenuators that I've got. Now, to buy these brand new, if you were obviously in the marketplace to purchase one of these as an organisation wishing to purchase it to use in the design or in laboratory environment, etc., I've been reliably informed, although I didn't pay that for this, and obviously the people in the know that purchase these on a regular basis told me that these are priced at about £2,000 each, these. So if you were in the marketplace to purchase one of those, that's what you're looking at for this Narda thumbwheel attenuator. £2,000 for that. It's unbelievable. But there again, it is meteorology grade components. So that's what you're paying for with meteorology. It's very, very expensive. Also made by the same company is a Type N one, and I've got a selection in this box here of all different types of attenuators. This again is made by Narda. This one has a lower frequency range, but it tells us it's DC to, I think it's 6 gigahertz, I think it is. Yeah, DC to 6 gigahertz. Now, sometimes it's hard on these attenuators to tell whether it's 3 dB or 30 dB, because as you'll see in a moment, when we look at the frequency ranges here for tolerance, there's actually a decimal point wedged in between the 0 and the 3, and it's so close that unless you looked at it with a magnifying glass, you wouldn't know. And if this was in the same box, which it is with the 30 dB one, if you miss the decimal point between the 3 and the 0, you could be selecting a 3 dB attenuator when you actually need 30 dBs, and you could convince yourself you've got 30 dBs in when you haven't, you've only got a 3. So I find that a little bit strange how they haven't taken care to widen the digits of the number so that you can clearly see the decimal point. And if it's 3 dB, for example, or 30 dB, because sometimes you do get attenuators where even though it's 3 dB, it'll be 3.0 dB, and I have some attenuators from Radial that are like that. So they've even put the decimal point on, because I think they made a range of attenuators where they were like 6.5 dBs or 3.5. They had the sort of 0.5 dBs in as well, so they had the obviously a decimal point, then another number after it. So depending on the number convention that Narda use, if it were a 3 dB, it might just show a 3, whereas other manufacturers would show 3.0, and that can get a little bit annoying when you're looking at the rating. But anyway, this is 3 to 6 gigahertz, plus or minus 0.5 dBs, but it doesn't tell us anywhere else about how much RF power it can take. So again, they've gone to all that trouble to print all that information, but they haven't actually said how much power it can take. But they've embossed Narda logo there, but no information about, you know, the RF power rating. So I'd have to look that up on the website, which is annoying, but that's how it is, you know, in the world of RF. Sometimes there's a lot of information provided on devices, other times there's very little. So again, in the selection box I've got here, we've got quite a few of the different types of attenuators. Again, lots and lots of different attenuator ranges. So again, that's another 30 dB, I think it is. Mainly all 30 dBs, these 130 dBs. Some of them have had some tape round them, so they're a bit more difficult. I see that's a 30 dB, so these all seem to be 30 dB attenuators. And then we've got some that are in 3 dBs to 3 gigahertz. I'll just have a look at this one then, just have a shufty at what this one's like. Let's have a look, see if we can get this end cap off. Probably not been off in years, so it'd be quite difficult to shift. Oops. All sorts of bits dropping out. Let's have a look here. 3 dB. Oh, so this is slightly different then in its design. Is this made by Narda, I wonder? Not sure. Again, lots of information printed on for the different frequencies and attenuation at different gigahertz frequencies. So that goes up to 3 gigahertz. Now it says on the body, it says made under license from Winchiel Engineering. So it's a Winchiel Marconi Instruments Limited. So this one's a Marconi Instruments Limited, and that's what they intended to do, were to, you know, put these sort of like labels on and do that. So again, that's another example. They put these caps on to stop dust and corrosion from setting in, because obviously that will affect the attenuation. So that's that. Now, as for other attenuators, as we say, we've got different types of attenuators. We've got small signal attenuators, And then we've got large signal attenuators, power attenuators, variable attenuators. You've already seen the thumbwheel one as well. There's loads of different types. So that's that, mainly to do with the Narda ones, which is in this box here. So I've got quite a few Narda ones in there, which are what I tend to store away when we need them. So before I look at the rest of them, let's have a look in here. So this is again, these are quite expensive. All these RF attenuators, they're not cheap at all, you know, and they're quite difficult to get hold of. It's taken me a long time to get these over many decades of collecting, you know, things. Just trying to find one that's not as manky to look at, but again, got some information there as to frequency and whereabouts on the frequency spectrum the attenuation would be. Tells you on it what the attenuation is. Again, this is the same. Marconi Instruments Limited, and then there's information there which you can barely see because it's under this sticky stuff. Find a better quality one. I wonder if that might tell us something. Let's have a look. Just have a look at that. These are being calibrated as well, but basically these go up to, according to what it says, 18 gigahertz. So these go up to 18 gigahertz, made by Marconi. So that's what all these are, 3 dBs, that particular one, 3 dBs attenuators. So those are mainly made by Marconi, N-type ones. So they're quite useful. They can handle up to a couple of watts of RF roughly. Not sure what's in this box. Oh, that's mixers and other bits and bobs in there, which we'll have a look at in another video. In here we've got another selection of RF attenuators. Now Greenpar made RF attenuators as well, but the Marconi attenuators that you've just seen and the Narda ones are the sort of the better quality ones, and Radial make RF attenuators. But at least on this you can clearly see they've gone to the trouble of not only telling you how many dBs they are, but also what the power rating is, 1 watt. And that's really good, because a lot of attenuators we've just seen with the others, even the Marconi ones and the Narda ones, don't tell you what the RF power rating is of them, and that's quite important obviously, otherwise you could burn them out quite easily. So, you know, if you do buy attenuators second hand or whatever, and that you don't know what the power rating is, then, you know, generally speaking, 1 watt for that kind of attenuator will do without causing any damage. But of course, if you really need to know what output power it should be, then you have to contact the manufacturer or whatever to find that out. Now, some of these attenuators that are made of metal on the outside like this, metal jackets, these generally can take more RF power, although don't take it for granted. And sometimes it will tell you on them what they are. Now, I sometimes get these that come my way where the label's been pulled off them or whatever, or come off. So I'll sweep them on the Marconi test set to find out the frequency and attenuation, and then I'll put a label on them. So you can do that. Again, BNC type attenuators as well. These are generally very low frequency, up to about 1 gigahertz more or less. This is a 12 dB, but these generally can only take milliwatts of power. And then we've got here some attenuators that have been used in various bits of equipment. Again, these are Narda ones, Now this one, I do believe, tells you a power rating on it, which is helpful. So it's a Narda micro pad. It's 9 dB attenuation, DC to 18 gigahertz, and it can take 2 watts. And it's a class, whatever that is. I can just about see it with my eyes, thereabouts. And then there's a part number on there as well. So that, again, is a very useful bit of information to have. So if you've got that kind of attenuator and you know what power it is, at least you can label it up with its frequency range and power in a box, so that you know what the hell it is, you know, when you need it. But this is a problem with a lot of these microwave and RF components these days, is that some of the information isn't on them. As you can see, there's quite a bit. Now, you do get attenuators that size that can handle as much as 3-4 watts as well, I've seen. I do have some here that are like that. So, and then there are others that can only handle a maximum of 1 watt. So again, be careful with the power ratings of them. But I'll just get another one out. I think there's these with the gold bands on. I'll look at these. And again, what's this one then? Who makes this? So it's an Omni Spectra then. So that's like Greenpar, MaCom. Tells you the model, tells you probably it's a 20 dB because it starts with the 20, although I don't know. DC to 4 gigahertz, so it's a 10 dB, look. But no information about how much power it can take. So again, you know, that's that would need to be researched. So there's quite a bit to it really with RF attenuators. These are quite useful in small signal applications, obviously, and that's where we'd use those. Obviously there are other types of RF attenuator as well, made by other manufacturers. Let's have a look at this one under my little magnifier. This is made by HP Microwave Incorporated in California, I think, and it tells us absolutely nothing at all about the attenuation or power rating or whatever. So that's obviously made for a particular piece of equipment, and it will be known up front what the part number versus attenuation is. So I could sweep that and then find out what, you know, the attenuation is on that kind of thing. And this is again this is a TNC version of it, but again it's 20 dBs. So we've got a TNC male and a TNC female, so this will generally be up to about 1 gigahertz in frequency. But it tells us there, oh hang on, there might be some information. Oh, it goes from 0 to 2 gigahertz, that one, you can just about see it there, just about 0 to 2 gigahertz at 10 dBs, 20 dBs rather, attenuation. So again, don't know who's made that, but at least they've gone to the trouble of telling us what the attenuation is, which is nice. It's very good of them. And then we move over to more sort of very high frequency, again, attenuators, such as this particular type. Now, these are quite a bit of data on them, obviously, so they're quite long tubes, quite heavy as well. These are again another quality component. I think these are made by Marconi, if I'm not at all wrong. Yeah, I think it is. Yeah, it's that Marconi company, part of them. And again, yeah, Marconi Instruments. So this is basically telling us that there's what the dB attenuation is at these different frequencies, so kilomegacycles. So up to 10 gigahertz, this particular one goes up to about, what is it, 6.2 dB at 10 gigahertz, and it's what is that 6.1 or 5 point, can't see, and then 5.7 at 1 gigahertz, 4 gigahertz, 10 gigahertz rating. And then on the other side we've got some more information, what type number is, CO number, etc., that kind of thing. So these, again, don't tell you what power they can take, but generally speaking, that size, you're probably talking about 5 watts of power maybe. But you know, again, it's a little bit of a guesswork really with some of these. Again, this is another type. It's got a test equipment number on it, so it's obviously been part of a quality control thing. So again, type N connectors on both ends, male and female, and then of course I can't get the plug in. And then what else have we got? Got this type of attenuator. Oh, it looks like it's a, I thought it was a 50 ohm load at first. So what's this one? 1 watt, somebody's crayoned on it. And then it says Greenpar 50 ohms. Talks about a serial number, attenuation. Is that 20 dB or 2 dB, something like that, 1 watt. So at least it gives you that information, you know, on it. So again, that will be used in a relatively small signal application. The nice thing as well about the Greenpar, if for the like the Greenpar kits for the RF adapters, you can undo them and change the ends on so that you can put different types of sockets on, like NPL2, SO239, BNC. This one's got an SMA on it, so you can change them, the inter-series adapters. You can do all that with Greenpar stuff, so it's quite flexible with the different adapters that you can put on the ends of them. And again, then we've got Suhner as well. That's another one, or Suhner, whatever you want to call themselves. These are again high quality components, and I think they're made in Germany, I think these. So we're talking, you know, DC to 1 gigahertz. This one's a 75 ohm one though. So that's particularly useful in AV applications, multiplexers, things like that run at 75 ohms rather than RF transmission systems, CATV, cable TV application, things like that. Broadcast areas, again, that's another Greenpar type of connector as well. More Suhner ones, so we've got those. And then we've got the obviously the splitters, the power splitters, made by Greenpar in this particular case. These are part of the inter-series again, so they unscrew. These have got obviously SMAs on. This is a wide band power splitter, so it obviously can handle quite a bit of frequency range from DC probably up to about a couple of gigahertz or thereabouts. But this is particularly good for testing amplifiers in parallel, so you could have 2 splitters, if you like, power splitters, so you'd have an amplifier in and out connecting between these 2, and the same at the bottom, 1 common input signal and then the summed up output. They can also be used in applications where, for example, you're testing a receiver's selectivity, where you have 2 signal generators, 1 connected to each of these, and then your receiver connected to this single port, and you can inject a different power signal on either port, or then, you know, close frequencies to check interference and selectivity of a receiver. You can also use them for distribution of antenna systems in buildings, such as with this one, again, Andrew. These are another big manufacturer in the RF world, Andrew Corporation. Manufacture everything from microwave dishes, antennas, waveguide components, RF coaxial cable, be it braided coax in the URM and series coaxial cables, as well as LDF series, heliax and solid coaxial cables that are used in everything from commercial, military and broadcast systems. They also make waveguides, waveguide components, and they also make RF connectors, in particular RF plugs and sockets of all the different types and sizes. So they are well renowned in the RF industry around Andrew. But again, this kind of power splitter will be used in a capacity where you would have a common input signal from, say, a repeater maybe even a radio communication system or a cellular repeater, and then you would distribute that output then to 3 different antennas in this case that could be in different parts of the building. It could be underground in a tunnel, a bunker. It could be in a subterranean environment, like for example a railway tunnel or something like that. That's where an RF signal from outside finds it difficult to penetrate. So these tend to be used in in-building solutions for that particular reason, for distribution of signals to application points, etc. So there's all sorts of different scenarios that these can be used in. They can be used in test equipment as well, where you sum in signals to 3 different outputs. You can use them in all kinds of different applications. This one's particularly rated though between a certain frequency range of 698 megahertz, I think it is, right the way up to 2.7 gigahertz. So that would be probably quite well suited for broadcast or cellular in that particular frequency range, as well as other microwave applications. So again, we've got loads of small signal attenuators. A lot of these are very difficult to see without a magnifying glass, to be honest, so made by all kinds of different companies, but these are generally used in small signal applications. Then we've got companies such as Mini Circuits, for example. So this box here, these are purchased in different attenuation ranges. So this particular one's got, these have got heat sinks on them. So a little like the smaller ones, these, but they've got the heat sink round them. And again, these are available in all different attenuation ranges. Now, Mini Circuits are a very good manufacturer. They're a bit like Narda and Radial and Suhner, and they're all, you know, make defence, meteorology grade and aerospace components. So we're talking, you know, top-notch quality. So again, 1 dB attenuation in this case, DC to 6 gigahertz, and then we've also got the power rating there, which is 2 watts. So we know we can stick 2 watts through there continuous and not burn it out. So, and of course, the reason why I purchased these in 1 dBs is because they're not a particularly sought after attenuation is 1 dB, but I like the fact that you can connect them together like this. So 3 of them would make 3 dBs at 2 watts. So, and these were cheaper to buy than just buying 1 3 dB attenuator, and it was just simply because of the fact that nobody really wants a 1 dB attenuator. But I saw past that and thought, well, hang on, we can use those anyway, because we can put them in 1 dB steps, if you like, multiples. So that's why I bought those. I can't say I've used them much, but you know, they're there if I need them. But they're good quality components, and I always recommend buying good quality things. Now you will see, particularly on some well-known sites, the Chinese are making copies of these, and that's one of the things that I wanted to talk about in this video, that is happening quite a lot now in the RF world. Not only with attenuators but RF power transistors and things like that, where we've got a situation where they're actually copying the logos of well-known companies like Narda, Mini Circuits, etc., and they're actually trying to make counterfeit components, and it's just one of those unfortunate things that you've got to be really careful where you purchase some of these attenuators from. And I've had some of these cheapo Chinese attenuators from, you know, some of these like AliExpress or whatever, just to see what they're like, and it'll say, you know, a 3 dB attenuator DC to 6 gigahertz, and when you put it on the Marconi test set and sweep it, or the spectrum analyzer, it's nothing like that. You know, it looks the part, you know, it looks really good, and but when you sweep it and you check it, it's not that at all, and the quality of the components look good, but internally they can't handle the power that they're rated to. The frequencies are all over the place with the response, so you've got to be really careful when you're buying things that you get them from the right places. So this here, for example, is a variable attenuator, this one. This is an ex-defence part, still got the NATO part number on it. This is a declassified microwave component, probably from a defence related application or test environment, some AT environment. But again, this is a rotary knob that's like got 10 turns on it, and before it stops, thereabouts. So that provides a very fine attenuation adjustment. Still turning now, it must have about 30 turns. There we are, stop now. So that's a nice little component as well, you know, and we can use that for little bits and bobs. And yeah, so, and of course, as well as that, in particular, like in RF power amplifiers, for example, this is a particular example. So this is a microwave RF power amplifier that's used in a microwave RF application. And then we've got in here an attenuator pad. So we've obviously got the driver and then the main PA transistor here. But in between we've got this KDI attenuator pad, which is what this device is. So we've an input and an output, and this is obviously rated at, at 3 dB. So we're having the power obviously that's going across it. So again, this is another application where attenuators are used in that capacity, where we're reducing the drive signal to an RF amplifier to obviously allow this RF amplifier not to be saturated or overloaded with its drive signal before then it's amplified and then sent out at great power. So again, these types of pads are used a lot in test equipment, such as radio test sets, things like that. So it'll be a device very similar to this, but it'll be rated at say 20 or 30 dBs, and that's what's behind the end socket on a lot of RF radio test sets. And obviously that's the kind of device that you can get. They make that style of package as well for load resistors as well, for RF loads. So that'll be bolted to a heatsink, and then you just have one tab and it'll be a 50 ohm load. But the good thing about these devices is that the lead lengths are short and the frequency ranges are very, very wide, and they can handle extreme amounts of power. So like a metal oxide substrate resistor, and so therefore the parasitic inductance and capacitance on these is so low, it means that you get a very high frequency range out of them and very high power handling as well. Some devices that are this size can handle as much as 150 watts RF. So that gives you an idea that as long as they're bolted down to a heatsink, that, you know, they can provide that kind of power at attenuation at very high levels of RF. So yeah, that's a little rundown, if you like, of those attenuators. Obviously, we've got companies like Narda again and Radial that manufacture this type of attenuators. This is 3 dBs rated at 16 watt. Internally within that, there will be probably a device which looks very similar to that there that we just looked at, bolted down to the heatsink inside, and you've got that kind of arrangement within it. So yeah, another little bit of thing, and then of course we get then to the higher power stuff, which is attenuators like this. This particular one goes up to a couple of gigahertz, that can handle about 10 watts. Then we've got sort of longer versions of it, and then that can handle a bit more power. Of course, we get to the heatsink types. Again, we get Narda make things like this as well. So, you know, these can handle a fair bit of power. And then we get to the real big boy stuff, which we've got from Bird Corporation, which I'm going to show, and other manufacturers for high power RF attenuators. Now when we get to high powered attenuators, they tend to be directional, do high powered attenuators. So for example, this is a typical example. This one here is has a defined connector and output here, and it does talk about 20 watts input, it says there, although it's output, so it can be used bidirectionally. But then on the other side, we've got the input here, which is 150 watts. So, you know, obviously, this again is another Marconi branded, because they're part of the Marconi brand. So, you know, this again is a very, very high-powered attenuator, 6 dBs attenuation. Now, this will sweep quite well. This has got a big metal oxide resistor element in it, and it'll handle 150 watts input, and generally right up to 6 gigahertz. So that's that. But again, there's inputs and outputs identified on them, because this is where, when we're dealing with high power, the resistive elements, it's like a T-pad by attenuator, you know, that you've got to get the input and output the right way around. So that's the output on this side and the input on that side. Again, N-type. And then it gives you the information. So this is part of Bird Corporation, which is a Bird through line attenuator. So this then gives you 20 dBs attenuation at 50 ohms, obviously. 25 watts though, only rated on this one. But it doesn't give us the frequency range on it, but it'll be up to about 1 gigahertz. That generally Bird stuff is generally rated to 1 gigahertz from what I've seen, most of it. This again is another Bird attenuator. This one here is much larger. Again, this one's rated up to 100 watts. I think it says there 100 watts. Yeah, 100 watts on that N-type. And then on the other side, we've got obviously an N-type male, and it doesn't give you much information really about that. You know, I'd have to look that up really on Bird's website. Normally there'd be information on it somewhere, but there isn't on this one, this particular one. So again, even though this is made by Bird, and I know it to be made by Bird, this has no information on it, whereas that has a lot of information on it. And, you know, again, even the same manufacturers we saw with Narda, sometimes they'll print information about power handling capacity and other times they won't. And it just seems a little bit disjointed to me why they never do that, you know, print that kind of information on, which seems a bit strange why they don't keep that continuity across them all. So yeah, this is where, again, you know, with attenuators like these, unless you've researched them and you know what the information is about them when you purchase, or if you buy them second hand, as I tend to do, knowing the information about them is quite useful. Obviously for ex-defence components, as I tend to have, they don't tend to have a lot of information available on the websites. So again, it can lead you a merry dance, and of course, you know, you end up then having to guess some of the time. But where you have to be careful with some of these RF attenuators as well is when you've got RF amplifiers that have got feedback circuits in them, and it's not just attenuators you've got to be careful with. It's when you're sweeping using RF test equipment, signal generators, things like that. You've got to be so careful when you're doing measurements that you make sure you take into account any feedback that's in a circuit, because there's quite a bit out there that can trip you up. I mean, this kind of RF amplifier here doesn't have a feedback in it, but you will see some amplifiers where they've got a resistor and a capacitor in series between the collector and the base of the transistor. And you can get, you know, if this is amplifying with a few hundred milliwatts input, 6 watts out to then drive that to set 15 watts to then drive this at 40 watts. You'll connect an attenuator here that's only rated, say, for 2 watts, and you then feed a signal generator into it to obviously then drive this amplifier. If it has a feedback arrangement on this device, that's 6 watts of RF in the feedback loop to give this a higher gain, then ends up also on the output of this, well, basically on the input to this amplifier. And so then you're feeding, well, two things could happen there. When you can burn your signal generator attenuator out, because obviously you're receiving a signal into the signal generator, reverse power that's higher than the step attenuator can take, it'll burn it out. Or alternatively, if you've got one of these attenuators there that's only rated to 1-2 watts, and you've got effectively 6 watts on that line when it's, you know, being in a feedback mode, then it'll burn that out. So you've got to be really careful, because some power amplifiers are designed that way. It's not often seen these days, but some of the older power amplifier boards did have feedback arrangements on the driver stages, and although in its in situ application, when it's in a piece of equipment where it's being driven with a low level RF signal, that doesn't matter in that scenario, because obviously it's effectively a transmitter going into an amplifier, and so any signals that are present on that line, that drive line, that is a feedback power, doesn't affect it really, whereas test equipment it does. So you've got to be so careful, and it is found on some amplifiers, you know. I mean, this Marconi amplifier here, that's got a feedback arrangement on some of these devices, although it's not particularly a worrisome thing in this scenario because of the low signal power. But again, this is a type of feedback here I'm talking about, where we've got the collector of a transistor feeding through a feed-through cap, through a resistor, back onto the base. So we've got an RF gain loop. And obviously on some amplifiers that you'll come across, this one's only a small signal feedback loop, so only going to get a few hundred milliwatts being fed back once this starts into conduction. Whereas on some amplifier designs, these first transistors that you come to can have as much as, you know, a few watts RF coupled back in a gain loop to get the gain on the transistors, and that can then damage the device that's feeding the signal into the input. Indeed, if you were measuring, if that came from a signal generator, it would damage the signal generator. So you've got to be so careful about when you're building amplifiers or testing them, whether they've got any feedback loops in. And there are ways then to get rid of that, like using isolators or circulators on the input, so that any reflected RF gets dumped back into a load rather than going to the source, which is your signal generator or whatever. So you can generally you know, sort that out, but you just have to be careful when you're doing testing. There's so many things, you know, that you can overlook, and you can end up causing yourself a lot of bother. Now, RF power amplifier modules like this, for example, somebody's had a go at this, but I bought this just for this part here. These don't tend to have any RF on the input, if you like, that's coming back as a feedback loop. So you just feed in, being wideband RF amplifiers, just feeding a low level RF into there in range of about, say, 100 milliwatts, and then you get like 30-40 watts or whatever coming out. And then your supply rails here, which then the first supply rail or second or third, some of these modules have multiple stages in them, particularly Mitsubishi, Toshiba and Motorola versions. So therefore you would have a transistor that you can control the supplies to the first, second stages, and then the third, fourth stages just be straight to the supply rail. And then you've got your RF out. These are good hybrid RF modules, but again, you wouldn't need to worry about a signal generator or whatever. And again, somebody's tried to make an attenuator here. I picked this up from an amateur radio rally some time ago, just for the heatsink and the RF module, which I can make things out of. And as well as that, biasing, you have to watch out for biasing, because some amplifiers, like this one for example, I think this is a Marconi amplifier as well, a test bed Marconi one, but you've got the input transformer balun, which is the coaxial cable with the two inners in it, transformer, an RF transformer, and then obviously your input, you've got a balun assembly, you've got two lots of power amplifiers that are paralleled with a common output then, to the RF out. But you've got bias on these fed through these biasing networks, as you can see, down to the base of the transistors. And on some designs, you know, if you're getting an amplifier out of a piece of equipment, for example, you may find that on some designs there isn't a blocking capacitor, and the DC bias will then be present on the input to that board. Now, the board that drives it may have a blocking capacitor on it, but if this is a module within a system and you remove this module, and these biasing networks here have got no isolation to then the RF input, because the isolation's on the next board, you'll remove this amplifier to then test it and connect it to a signal generator or an RF attenuator connected in here. That DC bias is going to go onto that attenuator, and it's going to be a possibly may burn it out depending on the value of the attenuator. Likewise, a signal generator as well, if feeding DC bias into a signal generator or a signal source, a sweep gen, whatever, and the DC bias could damage that instrument. So you've got to be very careful when you're looking at these designs. Obviously in this arrangement we've got an input to balance that goes straight on without any, there's no capacitor, goes straight onto this balance, so that's okay. We've got a capacitor there, look, and then a capacitor here, so the bias can't get back, so that's good. Then we've got obviously tuning caps. We've got parallel amplification with a DC bias, collector volts, DC bias, collector volts, which is obviously the supply of the amplifier, and then again we're decoupling again, and then feeding to the next stage, and so on and so forth before we get the output. So it all depends on the design and what you're testing, and again you may choose to have a attenuator on the input and attenuator on the output. So you've really got to know what RF powers you're dealing with, if there's any DC bias in, otherwise you could damage the attenuator or whatever the source instrument is as well. So there's all kinds of different scenarios, different things, but I think you get the gist of it now. But that's why, you know, it's always good to have a stock of RF attenuators as well. Now I will do a video on waveguide attenuators and waveguide components some other time. I didn't want to mix it with this particular video on the smaller attenuators. So we'll do some sweep measurements now and look at what sort of performance these attenuators give. Okay, well, what we've done now, we've set up the Marconi microwave radial test set. We have performed a calibration using the calibration standard. We've got a rated 18 GHz 50 ohm load, a Suhner load there on the end of this step attenuator. We've calibrated to the port, so obviously that will take care of this module sat here, so we're not using any cabling or anything like that. If we did have a cable, we'd calibrate to the end of the cable, but then in this case, because I'm testing it from 250 megahertz to 20 gigahertz, the cable itself that I have, these aerospace grade cables, are only rated to about 10 gigahertz or something like that, so it goes a bit crazy above that frequency. So rather than use cable and having to factor that in, I'm just connected straight to the port in the front of the microwave test set. So we've performed a calibration using the calibration standards. We've now attached the unit to the front of the reflection analyzer, and we're supporting it as well, just this pair of pliers underneath, because it's very heavy is that, and I didn't want it to strain the RF port. So that's what we've done there. Now at the moment on the test set, we're just looking at the Smith chart a moment there. We're obviously sweeping quite a wide frequency range. We're going from what is a VHF frequency down here at 250 megahertz, and we're stopping at 20 gigahertz. and the J we're just looking at here, which is the impedance of a device. Obviously we're on a 50 ohm system as highlighted in the bottom left, and this is the resistance that's currently being met. Now obviously this is over the entire frequency range of 250 megahertz to 20 gigahertz, so this is a Smith chart. 50 ohms is bang right on this line here that interjects from left to right, and on this curvature here that's going round, this one here, so that point right in the middle is 50 ohms, bang on. Obviously we can see this diagram is really quite useless in this context, because as we adjust the step attenuator and we move each of these attenuation steps, we can obviously see the resistance changes when I zoom back in to show you. And each time we change it, we're obviously changing, you know, it's a pi attenuator, so obviously each time we rotate the wheel, even in 1 dB steps, we can see that some minor changes take place, and then every 10 dB steps there's more major changes, as we can see it going around the Smith chart. So that indicates obviously that the resistance is changing as we revolve the wheels. Now in between the changes like that, that's a step in between, but it's not quite latched on from one step to the next, it's sort of in between the 10 dB steps. If I just make the wheel click again, so I've clicked into position, that's out of position, that's clicked again into the next step. So out of position, it doesn't terminate into a 50 ohm load in between the rotations. Some attenuators do that, and RF switches do that as well. There's quite a few of them that have that terminate into a 50 ohm in between the steps, or on an RF switch it'll dump into a 50 ohm load as well. And that's the type of thing that you get with these sort of attenuators as well, where you get like an internal load, which when you turn the step attenuator, what it does, instead of having an open circuit in between the steps, it dumps it into a 50 ohm load. So therefore it's, if you've got a VSWR alarm on a transmitter, for example, that's going through this, then in between, if you were to adjust that in between the steps, it could then trigger a VSWR alarm, because effectively the transmission line is going open circuit momentarily. And likewise with RF switches as well. Got an example of an RF switch here that's very similar, where we have an integral 50 ohm load within the device, and in between switching between the different ports, it makes before it breaks, so it'll dump into a 50 ohm load and then break the connection before it makes, and it'll do that. So you know, our switches operate in that format, and obviously these are small signal RF switches, quite a lot of them, because high powered signals you'd need quite a hefty 50 ohm load, but you'll see that on a lot of RF relays in test gear, that they'll dump into a 50 ohm load in between connecting to the next port. So it's the same with some of these RF attenuators that are step attenuators, where we've got a 50 ohm load and it's dumping it into a 50 ohm load between the steps. So there's always that continuity, especially when we're dealing with VSWR alarms as well. So this particular, I think it's JFW Industries manufactures these. These are very good step attenuators, wonderful. They are very, very good. So we'll have a look at those a bit later as well. But yeah, so as we're moving between the steps, you can see that it totally goes open circuit, and the Smith indicates that it's going all over the place. So, and we can look more closely at that as well, because when we look at the see if we can get a better picture onto that, perhaps on there instead might be better. that one. So as you can see there, we've got a bit of discrepancy from the 50 ohms at different frequencies. We're looking at that, we're at 15.4116 gigahertz, which is indicated here in the middle, and then as I move the marker, then we can see at different frequencies. In the top left, you'll be able to see the actual impedance up here, and as I rotate these steps, you can see that the resistance changes, the impedance alters each time I change a step, because obviously we're changing those resistor values in the step attenuator as we're going from one step to another. So each time I'm rotating, it's changing its dynamics. Now for VSWR, if I go back to measurements and then we select VSWR, and we've got a fairly consistent and good VSWR, even when I turn the, obviously in between again. Basically, to explain this graph, we're starting at 250 megahertz, which is here, and we're sweeping right the way up to 20 gigahertz, which is here. And the higher we have on the chart, the higher the VSWR, and the VSWR is indicated up here in the top left hand corner, and that's where the marker is now, that little T, which shows us what the marker represents right now at that position. So looking at it, if we go to let's have a look here, if I just alter this marker, so we can see that generally I think there's a little peak there which is 1.49 VSWR. So this is S11 we're measuring, and we've obviously got 1.49 ratio, which is quite good, and then obviously with a peak there, 1.50, that's at 12 gigahertz, and then it's fairly consistent actually. So you get to nearly 20 gigahertz, as you can see. Never really goes above 1.50 really, or 1.49, and then it suddenly launches and takes off there when it gets to about 20 gigahertz. So it's quite stable throughout its entire operating range when you think about it, you know. So it's pretty good dynamically. So I can't grumble at it, you know. It's obviously a very precision made device. So that just sort of proves really the quality of the component as well. If I look at phase, so that's the phase measurement, how many degrees out in phase it is, which will coincide with the Smith chart. Log magnitude, again, phase, VSWR, real, imaginary, and then polar Smith. So we can look at polar linear, polar log, and polar re, and that's Smith. So yeah, it's just a little rundown really, the sort of performance of the device. It's actually quite a good little device really. Quite pleased with it, and you know, again, another really good product made by Narda, so well worth having. Okay, so in this experiment what we've set up now is a slightly different experiment. We've got the scalar sensor connected to the output of the attenuator. The input of the attenuator is connected directly to the SIGGEN output that's sweeping from 10 megahertz to 20 gigahertz, and then we're measuring that then back into port A on the scalar analyzer on the readout. So basically what I'm going to do is just show the type of accuracy that there is across its range in regards to dBs of attenuation. We're generating 0 dBm level across that frequency. The performance is very good. Obviously it goes a little bit just wavy here, but I think a lot of that's to do with these RF connectors and adapters that I'm using, an SMA to an N, and likewise the other way, N to SMA. And although I've taught them up and everything, they're not really designed to go to 20 gigahertz, those particular connectors I've got. I think they're okay up to about 18 gigahertz, which is what this is designed to go to anyway. So, you know, obviously, prior to making that measurement, I connected the scaler probe directly to the RF out, and we got a very nice straight line at 0 dBm across. So we'll look at the insertion loss, which, as we can see, is about 0.4 dBm roughly, fluctuating around the 0.36 to 0.4 dBm insertion loss. So it's very small insertion loss, which I think, according to the spec sheet, if I'm not mistaken, let's just have a look, see what that says. It tells me what the insertion loss is. Let's see now. Basically, on the 0 dBm step, it says that it can have a 1 dB deviation. So, you know, it's well in its performance specification there. It doesn't say anything else on the spec sheet about its insertion loss. It just says attenuation, deviation. So that's really it. But yeah, so looking at it, if I adjust this attenuator in 1 dB steps, we'll be able to see. So I think that's 9 dBs. Alright, so we'll start right at the beginning then. So that's 0 dBs, that's basically couple through, and that's 1 dB step, 2 dB steps, 3 dB, 4, 5, 6, 7, 8 and 9, before then it goes back to 0 again. And then for the 10 dB steps, so that's the first of the 10 dB steps, 20 dB, and then 30 dB, and so I could go right up to 39 dBs obviously. In that case I can then go to 40, 45 dBs, 50, and then now we're at the 50 dB range. I can go right the way up to well into the 60s as well. Now that exceeds what the performance of the scaler probe can read. So, you know, it just shows the dynamic range of the instrument. This, I think it's about -65 dBm, something like that, when the scaler probe bottoms out. So as you can see, you know, it's a very good, well-performing attenuator. Okay, so there are many different types of attenuators, obviously. So one of the most common, or two common types, is the T attenuators, and then the what's called the pi attenuators. So basically the T attenuator is formed by having the signal path go into a resistor and then another resistor before then being led out to the output. And in between, at this junction in the centre, then we have another resistor which then comes down to the signal ground. So the signal ground will be the outer shell of the RF socket, plug, coax, etc. and that would then join to that resistor, and then we would have at that junction a resistor. So obviously in this context, these are good when both the input, the source impedance and the output impedance are the same. So if this is 50R and that's 50R, great. But if they're different, as in 50 into 75, 75 into 50, then that can all go to pot. So this is mainly meant for when the Z as impedance matches the output impedance. So this will be known as R1, that will be known as R1, and that will be known as R2. And basically in this formula, if we want to say a 10 dB attenuator, R1 would equal 26 ohms exactly, okay, and then we would have R2, that would be, for example, 35.1 ohms, okay. Now the problem is you're not going to get a 35.1 ohm resistor, and then you start piggybacking other resistors on. If you make them yourself, you'll realise this, but basically you then start having issues trying to get these values because they're not common values. Some of these resistors, depending on what attenuation we're wanting, depends on the values of these resistors, and there's a formula for doing this, which I'll not bore you of in this video. There's plenty of information on the internet and in textbooks and things, so it's not really a maths lesson. But as far as R1 and R2 values are concerned, they'll change depending on what attenuation we want. And so often, depending on what attenuation we want, some of these resistor values may lie in between what is commonly available, and naturally then to try and get those exact resistance values can be very, very challenging. And indeed it means that if you were to employ the nearest preferred value to these resistors, then you may not get exactly 10 dBs, obviously, because there will be a slight change. Likewise in pi attenuators, very similar, but we've got the signal ground and the active signal. We will then connect that straight in then to a resistor, single resistor, which will then go to the output. We would then have a resistor again on the signal input to the signal ground, and a resistor then on the output from the signal out to the signal ground. The signal ground again, which is the outer shell of the coaxial cable, plug socket, etc., from the signal source, that would then be connected together in that. So this would be a pi configuration. There are other types of attenuators as well, where we have a pin diode, and they're mainly current devices in this context. So we would have, for example, a feed-through capacitor, RFC. So that will be a device which would have it's like a cylindrical device with a conductor at either end, where we'd solder a wire on then to a power supply, and that would then, once it reaches the inside of the enclosure, will be fed into a radio frequency choke. That would then be fed onto the RF line, and this would have an input blocking capacitor for the DC bias. That would then go to the RF input, and then upon that meeting there, we would have the silicon device itself, which is the pin diode. So this is known as a PIN diode. And then on the output, we would have a resistor, which would then go to signal ground or negative, because obviously the positive and negative line will then connect to what will be signal ground. So the two terminals for the PSU, one will connect down here to the signal ground, which is a negative. And then we would have a DC bias blocking capacitor on the output, which would then obviously go to what is our RF socket. And that's basically that. So this is obviously a current device. So as we increase the current flow through this device, then naturally the RF signal, which is present on the input here, will change its attenuation. So therefore this device then, depending on how much current's flowing through it, then the RF signal will change from small amplitude to a larger amplitude to match what's coming in. So it all depends on what's, you know, going on with the current here. and so when there's no current flowing in the circuit, then we've got maximum attenuation. So a signal coming in will get blocked by the device, there'll be no output. And as we finally adjust the current that's going onto this device, then we would obviously then see the RF allowed through ever such a small amount, and depending on how much current we start to flow, then we would see a larger RF signal coming out. And so if we finally adjust the current that's available to this diode, then we can adjust the RF attenuation output in comparison to what's coming in on the input. And so we can change the output quite easily and finally adjust it. The problem with these attenuators is that they are designed generally, because of the capacitive and inductive components, they are designed for particular frequency bands. So they're not very wide banded. You can get them quite wide banded. They're very expensive though to manufacture, and sometimes the cost of them outweighs the benefit. But they also have other issues as well, where you can obviously get signal mixing and things like that can occur in the pin diode. The pin diode can suffer with heat problems, because naturally the RF power that's passing through, if it's in a high power application, can then cause the diode to heat up, and capacitors and the capacitive and inductive effects, the LC constants, these then can also affect the way that harmonics can interact going through the attenuator. And so there's all kinds of other trade-offs that need to be taken into consideration with this kind of attenuator. But generally speaking, they are actually quite good. But you can get other issues as well that you won't find with a resistive attenuator. But obviously the advantage of these is the variable attenuators, and they can be used to switch RF on or off or attenuate it appropriately. In this capacity, in this particular type of attenuator, whether it's a T-type or a Pi-type, generally how these are manufactured is they have a like a resistive slab, if you like, in the middle, like a core, but like what's inside a pencil. And this resistive material effectively forms a resistor in this capacity. And then round the outside of that, if you like, there is a disc which goes round it. And this also has, between its inner part where it connects here and outer part, it has resistive materials all the way around it, which then go to the outer shell of the device. And then we would have obviously what would be the RF connector then on the outside of it, and naturally that's basically that. So it would allow dissipation of heat through to the outer shell being made of metal, and that would obviously allow heat to dissipate off these fins. There are also other variants of it as well, where using metal oxide. I've seen that, I think this type, we did a repair video once on this type of attenuator, and this basically is just a metal oxide substrate. It's like a flat glass cut piece of metal oxide, gigantic piece, which is sandwiched between the heatsink, and the two heatsink halves clamp it like a clamshell, and then you basically got resistive elements on it. So it's basically a flat conductive metal oxide resistor, and on it, engraved into it, etched into it, because that's how they can change, they're these resistive pads, which are then obviously all in series and parallel configurations to the ground. There's like a gold edge which simulates the ground, signal ground on the outside, and then they're part of this arrangement, if you like, so that the double up on resistors and pads all the way down to what is the signal in versus signal out. And because it's on a metal oxide substrate, It's like a glass. It's normally coloured white, and then you've got these resistors that are part of the etch them. So they actually, to change the values of resistors, the material that they put down, the resistance material, is sort of shaved in places so that it gets the precise values of resistance for the attenuator, for either the pi or t type, depending on how it's configured. And so what happens is, because it's on a metal oxide substrate, like a thin glass type, that's all I can describe it as, like a tile, then basically the heat, as these resistors get hot with 150 watts, in this case, this is rated to 150 watts input. So the RF power coming in warms these up, obviously, these resistors, and because they're bonded to this metal oxide semiconductor sort of wafer, it conducts heat away to the outer edges of the metal oxide tile, and that then is clamshelled into the attenuator, so it then wicks the heat away, and that's when obviously you can then, these heatsink fins, if you like, are on the outside. Now I've swept this particular device. This is a Marconi one again, but this device goes up to about 6 gigahertz and can do 150 watts. So there's all sorts of different types of attenuators. Obviously, if you're using carbon resistors and things to make attenuators, then I've known people shave some of the resistors with a file to try and get precise values for the points, so that they're measuring accurately, and then they can produce a correct dB attenuation. Using carbon resistors, you might get up to 1 watt maybe handling power, but carbon resistors do change the values as they get hot. So naturally, depending on what temperature rating they are and the precision values, the attenuation could change slightly. You can't obviously find it easy to wick heat away from a carbon resistor like you can with a metal oxide variant of it. And then, of course, not forgetting that, we have the fixed film type resistors, which are very similar to this design, where it's basically a pad in and out with a heatsink sort of configuration, which we showed you in the amplifier earlier on in the video, where we've got an in and an out. And that you can buy them in different dBs. It's often stamped on them. KDI make them, and various other manufacturers around the world. Again, these generally are quite high powered rating. They're very, very stable. But again, it uses that principle like the metal oxide down here, because that's effectively what it is. It's like a metal oxide semiconductor on a beryllium copper base to wick the heat away. And that's another thing as well that I just need to briefly speak about with these RF attenuators. They all have, generally speaking, no matter what type you buy, this type or some of these others, they're quite dangerous in the fact that the way that they conduct the heat away uses beryllium copper. And beryllium oxide in particular is very, very bad for your health. Particularly if it's machined or brought into a dust, gets into your lungs, and it causes berylliosis, I think it's called. It's a bit like mesothelioma, which is asbestos, which gets into the lung and then obviously causes lung cancer, and it can cause all kinds of other respiratory illnesses as well, and it's very nasty stuff, is beryllium. Beryllium oxide is found in RF power transistors, RF attenuators and other RF semiconductors. So you've got to be very careful when you're working machining or messing about with RF components that you don't break it up into a dust or machine it or smash it, that kind of thing. You could breathe that beryllium dust in. So that's why you've got to be very careful about it, and I think it does tell you that anyway on the on them, a lot of these attenuators, about them containing beryllium oxide. So you've got to be very careful with that. Now on valves like 4CX250B valves from LMAC, it's like a pink substance. It's like a bluey pink substance. It's used in the insulator between the anode and cathode. and it's often like a what's the best way to describe it? It just looks like a ceramic insulator, but it's often pink or like a bluey colour, a very light blue. And again, that's used to wick the heat away and to provide electrical insulation. And it's you can often get beryllium impregnated ceramics as well, where they're used in hot applications, in valves or in other RF componentry, and the beryllium is used in a small mix content, if you like, in the substrate that the RF device or conductor will be used in, and it's just to get the heat away more effectively, but it's not wholly beryllium. But in RF transistors and in attenuators, there's a lot of beryllium in them, beryllium oxide, and it's like asbestos products. Some asbestos products only have a little bit of asbestos in to give it its feature, its capability, what it was used in. And other products had a lot of asbestos in because you needed that insulating property. Whereas for heat insulation, whereas for beryllium it's a very similar thing, where some components have a lot of it in, beryllium oxide, and some components have only a little bit in. But either way, it's very bad for your health, and so you've always got to make sure that if you damage an RF component, that you don't create dust from it, and use special cleaning rags and throw them away after you've used them, or if you get an RF transistor where somebody smashed it in or whatever, that you don't you bag it in a plastic bag and you dispose of it properly as in toxic waste, because that's what it is. It's a toxic compound, so you've got to be very careful with that. Okay, so this type of RF power divider is a resistive power divider, and as you'll also see in other videos that I do and will be doing, that you can get different types of power dividers and splitters, like Doherty, Wilkinson, for example. It uses strip lines or balance transformers, basically RF transformers, to be able to couple to multiple signal outputs or multiple signal inputs, and you can use all kinds of different configurations. But in the context of this video, there's also resistive power dividers as well, where they're obviously very wide frequency range, whereas a Wilkinson and Doherty combined arrangements basically use strip lines or RF balance transformers, and they're obviously dependent on frequency as to their electrical wavelength. And in this context, you tend to find resistive power dividers are extremely wide banded and very useful, and that's why Greenpar made this device. And it looks like how they've machined it, I don't know, but it's like an infill. It's probably potted. There's no sort of opening to get into it. This is a nice one because, like a lot of things with Greenpar, they made it so that the inter-series adapters could screw and unscrew from them, so you can change the gender of the RF connectors. So Greenpar was sort of head of the day really with that in comparison to other manufacturers. They allowed that user to choose whether they wanted, SMAs, Ns, whatever sex of connector they wanted on there. That was part of their design methodology. But in this case, in the resistive power splitter context, we've obviously got 3 ports on this device, as in a pyramid, so in this context, we would have a resistor that would connect from each port going this way, like that, and then we would have another one in that context. So no matter which port we're using, we're always going to get that same kind of split. That's why it's not labelled up, in, out, it's all equal across it. And so therefore these resistors are inset within this device, and depending on it does give us some information. It tells us that it's not only a power divider, but it's a 50 ohm impedance at 1 watt. So these resistors are capable of taking 1 watts of RF power. So you could feed a signal in on any of these ports basically, and you would then obviously be able to divide the power up equally between the ports. So that's a type of resistive power divider. It's very useful in lots of different applications. You know, you could feed that off, for example, to 2 different signal sources, and you could then have one common output, or you could feed one common input in and then have 2 outputs, you know, which would then lead off to, for example, in this capacity, you could put it to, say, a modulation meter or a frequency counter, you know. So you could do that. You could also feed one port off to a spectrum analyzer, another port off to a frequency counter. You could do all manner of things. You could even feed it to 2 different antennas, for example. There's lots and lots of applications that you can use this in. And of course you can use it as well in conformance testing. You can have 2 power amplifiers, low power amplifiers, that connect to either port in parallel, and then have another one then on the input as well. So you've got 2. So you can basically have it in this configuration where you've got 2 RFPAs or 2 signal sources, for example. Feed them in then to that splitter arrangement that we've just talked about, and which has obviously got the 3rd port there, a resistor down to there, a resistor to there. So that would be a common output to an antenna or whatever. And then the input the same again, fed to each port. Then obviously we've got a combined input. So again, then we would feed that then obviously our signal source coming in. So you can do all kinds of things with them, you know. They're very flexible, and you can turn them into whatever you want, really, you know. So that's why I always keep them, because they're quite useful in that context. So there's all kinds of really useful little things like that, little gadgets, and you can really, you know, get a lot of use out of components like this in that kind of application. Then of course we've got the variable attenuators, which we talked about earlier, which are in particularly, depending on what configuration they're in, we'll talk about that next. Okay, so I've looked up this device, which is a variable attenuator. It has SMAs on the input and output. It's made by a company called ARA in New York, USA. I've looked at this online just to see its specification. It says basically it's a 5 watts on average, 3 kilowatts peak, it says. That's obviously pulsed, but 5 watts CW. Variable attenuator, up to 30 dBs attenuation range, and it achieves that within about 20 turns, full turns of this dial. But anyway, basically on their website it says that it's got a frequency range of, according to the info I'm reading now, 8 to 18 gigahertz. So that's, you know, the amount of attenuation that it can do between that frequency. So that's an example where you can finally adjust the attenuation rather than have it in steps with a step attenuator. You know, obviously something like this, you can only achieve predetermined steps, and therefore, you know, and this can only take about 1 watt or 2 watts of power, whereas this can take 5 watts, and it's just a very fine variable adjustment. Now they do a different version of this as well. It's got a digital counter. It's like a spinning wheel sort of mechanical counter, so you can finally calibrate the position that it needs to be in for certain attenuation levels. But this one doesn't have that. It's just their base model. So this will probably have a metal oxide semiconductor material, just like we were discussing earlier in the other type of attenuator, and it'll have a sliding plunger, a shaft which goes in and out of this device, and it'll slide probably like gold fingers on a slider, to adjust the attenuation. So you'll have the resistance material on a metal oxide substrate bonded down to this shell, probably as a heat sink, and then there'll be two beryllium copper coated fingers on this plunger, which then go up and down that sliding of resistance material to change its values. So in other words, you can adjust the attenuation. So probably these were very expensive to buy. I'm not sure how much, but I bet they weren't cheap, considering the power handling is 5 watts continuous and 3 kilowatts peak, obviously pulsed in a radar application. So look after that. But yeah, obviously all these little interesting components, these little changes of design and device, etc., and all these different components. Anyway, we'll obviously give this a sweep on the Marconi microwave test set now and see what kind of attenuation levels it gives, and how stable it is over its frequency range. Okay, we've set up an experiment now where we've got the RF output connected to one side of this device, and then the RF output of the test set into the input of the device, the output of the device into the scalar probe for the network analyzer, which is connected on port A. We've done a calibration of the power sensor before we've done this measurement. We're currently sweeping on the test set. We've got a measurement now showing on the main display when I can hold the camera still. So we've got 8 gigahertz on the far left we're starting from, which is just here on the left side of the screen, and we have got a maximum frequency on the right side of the screen of 18 gigahertz. So that's the rated specification for this device according to what it says on the website. We have an RF power of 0 dBm, which has been on the source. If I change to the source and set output power, which is there, you can see it says 0 dBm up there. So that's the reference level in essence that we're looking at. And I'm back on the markers now. So basically, if I turn the control to it's at the bottom now, is that it's like a minus 1.85 dBm level at the moment, as we can see there up in the top left hand corner in the red box. So that's the sort of a system losses, if you like, or it's minimum attenuation that it'll go to. Now if I adjust it now, start turning the pot right the way around, you can start to see that it's beginning to fall off, and then obviously it's got more of attenuation on the left at the lower frequencies, or less of attenuation I should say on the left at the lower frequencies than it has on the right hand side of the waveform. And then we're into the noise floor of the instrument, so you know that gives you an idea. But that will be there, just about there, minus 30 dBm, which is its rated specification, 30 dBm, 30 dB's attenuation. So that shows you that. Anyway, what I did, just in case I messed it up, I swapped that round the other way, so the input and output were basically opposite. It's not marked on the device input output, and on the website it doesn't show that having been directional in any way. As you can see with the measurement, we've still got that sort of 1.1 dBs of system losses, if you like. So it's about its insertion loss is about a dB, which is pretty standard really for many devices in this class. But again, when I adjust it, because I've turned it the other way around now, and you get about 10 turns though on it before it starts to adjust. But anyway, as you can see, it's more responsive sort of at this end, and it tails up at that end, so you get less attenuation at that frequency. Now if I adjust my markers and then change that, so what frequency is that then? It roughly starts to be more linear at around about 11 gigahertz. So between 11 to 18 gigahertz it's actually quite flat in its response, but between 8 to 11 gigahertz it's obviously got that downward trend. So it's a bit sketchy in that part of the band, I think. But anyway, just keep reducing it. It sort of keeps that linearity really all the way down till we start getting into the instrument noise floor around about minus 65 dBm roughly, or minus 60ish roughly, 58. So yeah, it's not very good that really, I don't think, considering its you know, its rated specification is 8 to 18 gigahertz. So it seems a bit strange to me, does that? And so that's a minimum level of attenuation there that I can achieve. I'll just you get a bit of a fine adjustment for another 10 turns, and then that's its minimum level. So a bit strange is that. I don't know why that is. It's obviously a way it's been manufactured, designed, etc. But such is life. Anyway, at least we've had a look at that and we've seen how that works. So we've got this attenuator on now, this big 3 dB one. It says it's 3 dBs just at the top. I had to remove a label that were protecting it, but basically it's 3 dB rating. Not sure who made it, to be honest with you. MFN, I'm not sure who that is. There's no manufacturer information on it anyway. So anyway, it's a 3 dB attenuator. The system losses of all the coaxial cable connectors and everything, with this measured outside this measurement, in other words we connected that end to that end and just with a probe on the end of a coax, it was about just under 1 dB of loss, or thereabouts, a dB of loss. So now we've got it in situ. I could have zeroed that out, but I always like to show things as they are and factor that into the measurement. So here we've got a 10 megahertz to 5 gigahertz frequency sweep, and we can see in the top left hand corner it's measuring 4.13 dBm at what is 2 gigahertz at the moment, where the marker is, which is this little square here. Now obviously it's quite wide banded is this, it's able to provide a 3 dB attenuation, because don't forget we've got approximately 1 dB of losses in the system. So it's 3 dBs, which is rated on the device as to what it is, 3 dBs, so that's correct. Now we could just see how far we can push its frequency. I could put a stop frequency in of 10 gigahertz, and then we can roughly see where it starts all going a bit funny. But as we can see, I think if I go back to my markers and I adjust my marker now, and it starts to fall off round about there, I'd say. It's a bit sketchy at this point, although it's still maintaining good attenuation. Then it starts going all funny at there, obviously. So if we were to just look at this area here, then we're looking around about 4.2 gigahertz. So that's pretty good. Now I think it's fairly uniform, although we get quite a lot of distortions in it as we're going along there. So well, we'll take it to its extreme then. We're at 4.23 gigahertz. Let's see what it does when we increase the to there. It starts getting a bit funny. So really right up to about 6 gigahertz it's quite good, quite usable up to 6 gigahertz. It's still maintaining its attenuation, and then I think from roughly 6 gigahertz that's when things start to go a bit strange, you know. It starts dithering about a bit. Whether it can handle much RF power up at that frequency range, probably can. But yeah, it's quite usable up to about 6 gigahertz is that, roughly. But I wouldn't push my luck with it. Definitely not. It's not designed for that. But up to 1 gigahertz I'd use it, possibly 2 gigahertz. I'd be quite happy at that. Now this one appears to be faulty. This is a Bird term line attenuator. It has some information on it which tells us what attenuation. It says 20 dBs, and it basically says 25 watts. We've got an input, and then obviously on the other side an output marked, but I'm sweeping now between, on the microwave test set, between what would be 10 megahertz to 10 gigahertz. But even if I do the stop frequency, say 1 gigahertz, and the start frequency is obviously at 10 megahertz still. If we go to the markers, we can see that it's actually about 5 dBs off or 5 dBs out. It's actually 29 dBs at 1 gigahertz, which is on the far right hand side of the screen. And then if we adjust the marker, and then it falls off even more at 40-50 dBs into the noise floor. So I think we've got an open circuit RF connection on this, because obviously as we increase in frequency, the coupling factor, you know, will allow higher frequencies to couple across. So we might have a dodgy RF connection in this device. I've checked all the connectors, everything are very tight, and they're all very secure, but this is not performing as it should be. I actually bought this from a radio ham rally, so the chances are that there's two things could have happened. Either the connector's got a fault at either end, as we had with the other attenuator. If you watch me Aeroflex spectrum analyzer repair, we were checking spectrum analyzer demonstration, we were checking an RF attenuator, and we found that we had an open circuit connector in one end when we did the demonstration of the tracking generator on the Aeroflex spectrum analyzer. So if you watch that video you'll see that. But this has got very similar characteristics in that as we increase the frequency, the attenuation comes more or less within line as to what it actually should be. So I'm going to take these connectors off next and have a look in the ends of these, but it could be we've got an open circuit connection somewhere, or it could be that somebody's fed way too much RF power up it and it's burned out the resistor section inside. So we'll have a look, see what we can find. Okay, I've had the RF connectors off and everything. They all look okay, to be honest. Can't see any problems with those. I've checked them electrically as well with the multimeter, and they're all fully. The pins are not broken in the socket, so you know it's not as if it's that's causing the problem. So yeah, it's because sometimes these little pins break in there with the back part, and then it's open circuit, and then it obviously couples at higher frequencies, so you get the situation that we've just found. So I think this is broken internally actually. Now obviously this has got beryllium oxide in it, extremely toxic, so I didn't really want to start hacking it to bits to get in it, but I can't get that module out anyway in the middle. I've tried pushing on this PTFE insulator here, but basically that's the RF in output whatever element there that mates with the center pin. That just goes in there like that, it just pushes in, and that's all correct. And again on the other side same again, but even I can't push it out, it's stuck in, it's obviously glued in or whatever, potted in. So I'm afraid that's bin fodder. That's what happens when you buy something from radio rallies, that often they're broken, they're duff, buyer beware. So I've picked this up. I don't know how much I paid for it, probably not paid a lot for it because I'm quite a cheapskate, but this is well and truly knackered, can't use it, so that'll have to go in the bin. I'll throw it away in toxic waste, and this will be retained for future repairs, these two, because they'll be quite useful for that, So I'll bag this, throw it in toxic waste, and then obviously get these retained for other things. So it's a shame that either it's been banged and dropped and it's come uncoupled inside. That characteristic that we saw where the frequency low down was extremely highly attenuated versus it then increasing going up to near the level that it should be, give or take a few dBs, at higher frequencies is synonymous of the coupling effect when two RF pass, if you like, have an air gap. So obviously the transform effect works at high frequencies, hence the reason why we could recover the signal at high frequencies. Normally I'd say if it was burned out, as in somebody put too much RF power up it, then it would probably be okay, more linear across its entire frequency range, but it would have a much higher or lesser RF attenuation because the resistive elements would have been burned or damaged, but yet its frequency response wouldn't be great, but it would be a lot better than as it is now. So this looks to me like as if the actual resistive element inside is open circuit or broken, and that's the reason why it falls off at the lower frequencies, because it's at the higher frequencies it's able to transform across a broken connection or a gap in the conductor, particularly at gigahertz frequencies. So yeah, it's just a shame really that that's damaged. No use. Okay, so this is another attenuator that we've connected up, and just to look at this one, I think this is about 15 dBs, and as we can see it's got that nice uniform linear straight line from 10 megs to 1 gigahertz, so that's fully functional. So we'll have a look at this other one here, which is quite an old attenuator that I picked up from a Hamfest, and see whether that works. So I connected this older attenuator that I've had in a box that I found, and it looks okay, it's just a bit tarnished. It's a Marconi one, it says. Anyway, looking at the performance, it's a bit like the other one, the bird through line one, term line, that we looked at earlier, where at the low frequencies it's in the noise floor, but as the frequency gets higher, the transform across a broken gap, air gap if you like, occurs, and then we get some kind of a response, even though it's well below what it should be, but you can see it's got the same characteristics. So this is a problem with these, you see. If you drop them on the floor, then they're easy to break. So that's why you've got to look after attenuators if you've got them, and not subject them to violent shock or falling on the floor. And often, you know, with them being cylindrical like this, it can roll off a bench onto the floor, and then that causes damage to them internally, and then you end up with that, and the unfortunate case there that attenuator is no longer working. Now if I bang it a few times just to see whether it alters its performance a little bit, it might do, but I can't see much change there. So it's obviously damaged internally. So that's two attenuators I've found out of a box of old stuff I had floating about that are defective. So there you go. That's a little lesson, just to look after your attenuator, make sure they're packaged up and boxed and protected from shock and damage, you know. So with that, I think we'll move on to doing some more measurements now with transceivers, and then show an example of one of these being used with a spectrum analyzer and a transmitter. Okay, so what we've done in this test now is we've got a Calmus power amplifier. We're driving it with a signal at 500 megahertz at 0 dBm. So that's been fed on the output all the way down into the input. Coming out then, we're going back up to the Marconi radial test set, and as you can see we're displaying a power of 4.23 watts at 500 megahertz, which is the test frequency we're using. So the idea now is to attenuate this and connect it to the spectrum analyzer, but also program the spectrum analyzer with the attenuation that we're going to put in, so that it reads the fundamental power rather than after the attenuation has occurred. So that's what we're going to do next. Okay, so in this quick scenario, we've got 3 dB attenuator and another 3 dB attenuator. So we're starting about 4.5 watts. For every 3 dBs we attenuate the signal, we're half the power. So we've obviously gone, in this case, I've put the two attenuators together, and then I've put this absorption wave meter on the 10 watt scale. So 1 watt would be here, down there, just at that moment there, that little segment. So that's 1 watt. And in order for the spectrum analyzer to read that signal, it has to be less than 1 watt. Otherwise it'll overload the spectrum analyzer. So this is just a little demonstration just to show you what the attenuation does and how we look at that. And looking at now the signal's on, we're getting 1 watt. So if you think about it, so we're doing about 4.5 watts roughly. That 3 dB attenuator will halve the power, because for every 3 dBs we attenuate, we're halving the power. So we've halved from 2 watts down to 2 watts from 4. We've halved 4 down to 2. We've got another 3 dB attenuator, so 2 watts that's leaving here is halved again to 1 watt, and that's the reason why we're reading that power there. So 6 dBs of total attenuation. So we're now down to 1 watt. Obviously this is still too high. This is right on the limits of what the spectrum analyzer can take. So we've got to attenuate this furthermore in order to be in a safe limit for the spectrum analyzer. So that's what we'll do now. So what we've done now is we've got 3 dB making 6, another 3D making 9 dBs. So we started at 4 watts coming in. That's got reduced to 2 watts. Now because we're halving it again by another 3 dBs, that reduces 2 watts to 1 watt. Now we've got to the stage where these smaller attenuators can handle 1 watt, because obviously prior to that these can't handle more than 1 watt in this particular case. So we need to reduce it down so another attenuator of lower power handling can then be employed. And this is where this gives us 9 dBs of total attenuation from there to there. So hence the reason why we're now reading 500 milliwatts, which is at the particular scale that we've got on this absorption wave meter. So we've got 1 watt, 500 milliwatts. It's just reading a little bit below. This particular Rhode meter isn't nowhere near as accurate as the Marconi radial test set, obviously, but I just wanted to keep it basic so people could understand it more simply. Now obviously I've shown you this for that reason, because we start with the highest power attenuator possible beforehand. We step down to a lower power, medium power, and then so forth. You wouldn't put this before it. If it was say a 20 dB attenuator, to get the most attenuation, because this is only rated at quite low power, you wouldn't put that at the beginning, because this can't handle the power. So you've always got to have a situation where we have a highest power attenuator capable in the system first, followed by the next down, and you must always make sure that the output power from the first attenuator doesn't exceed the input power of this second attenuator, and likewise the third attenuator mustn't receive an input power greater than it can take as well. So this is why you step them in. And of course you can get attenuators that are just like 30 dB that can handle 300 watts, just that size, and it does away with all that. But I wanted to show this so that people who have different types of attenuators, or maybe I don't have a full complement set of different attenuators, can know how to connect them up. And now we're in a safe level then for the spectrum analyzer, because the maximum level that we can put into that is 1 watts. That's it, 1 watt, no more. And I wouldn't be happy driving the spectrum analyzer at 1 watt. So we're giving it 50% less than its rated maximum now in order to measure the signal that's coming from this transmitter. Okay, so now we're ready to set up the spectrum analyzer to take account of the attenuation, and we'll get it to display RF power as well. So first of all, we'll set the frequency, the center frequency to 500 megahertz. We'll set the span to 1 megahertz. we'll check that the information's there in the bottom of the display, which it is 500 megahertz, span at 1 megahertz. Then we'll go to amplitude, and under amplitude you'll notice it says reference level. Well, if we've got a 0 dBm signal coming in here and the reference level is 0 dBm, it means that right at the top line will be 0 dBm. So if we put a 0 dBm signal, the signal will reach the top line and come down. You can leave it at that if you want, but I prefer to have 10 dBm so that it puts it a graticule below roughly. Then what we do is we go over to where it says reference level offset, and that's where we enter 9 dBs, because that's the level of attenuation that we've got. So we go there. Currently it's set at 0 dBm, so we put 9 dBm in. And now that's set the spectrum analyzer up to take account of any signal coming in here. Whatever it reads on the display when we go back to our measurement, that will take into account that 9 dB attenuation, and it will effectively give us the same reading as what will be at the beginning of the attenuation. In other words, what's coming directly out the transmitter. So with that, now if we go to page 3, you can set up under amplitude, page 3, units. So at the moment it's reading in dBm. We can change that to watts. Okay, so that means now it's reading obviously watts instead of dBm. If we want to do that, obviously you can leave it into dBm if you think dBm is better for you. Okay, so when we go back now to markers, and we've got basically just to check it all, we've got a signal that we're going to apply, which is 0 dBm as a test source, just to show you. And it obviously should read about 1 milliwatt based on the accuracy of the signal generator that I'm using. So now, because we've introduced that factor of reference level offset of 9 dBs, it's reading 9 dBs more than it should be, you see. So that's the reason why that's reading high. So if that was set back amplitude level, and we went to page 2 again, reference level offset, put that back to 0 dBm, then the signal is reading 1 milliwatt, just over 1 milliwatt in this case. So 0 dBm is 1 milliwatt. Okay, so we'll reintroduce that reference level offset again of 9 dBs, so that when we introduce the transmitter, then that factors in the attenuation, and the marker level will indicate the transmitter's power rather than what comes out the attenuator. So that's what we're going to do now. So now we'll hook up the transmitter to this port. We're ready to make the measurement. Okay, with the amplifier cooling off now, it does generally between about 7 watts and about 4 watts, depending on you know, what the temperature is of the amplifier, but I've kept it quite uniform so that at least then it'll take account of the temperature variances, because the amplifier slightly alters its gain, its output level, as the temperature increases. Okay, we've connected up the attenuator section here. That's all fully connected in, ready to make the measurement, and we're ready to go. So what we'll do now is we'll connect up the power, the RF power. Now don't worry if you've not set up the spectrum analyzer to do this before. This tutorial sort of gives you an idea on this particular model, but most spectrum analyzers are very similar to this. The other thing that you might need to adjust is the input attenuator, because obviously the signal that we were looking at earlier was 0 dBm and it was at the top of the scale. So now we're introducing a much higher level in there, then naturally that signal will be way off the top of the graticules at the top line. So you would need to adjust these input attenuators to maximum probably in order to display the signal properly. So that's normal, but that comes with experience of setting up spectrum analyzers. So here we go. So now we've got the signal and it's to the top line. So we've got the maximum level of attenuation on at the moment. It won't attenuate that any further, so that's showing us that we're within tolerance now and limit of the below the limits of the input arrangement on the test set. Now when you look at the signal level, if I zoom in for you, now it's telling us what the input power is to what would be the attenuator, and as you can see there, if I can just zoom in a bit better for you, it shows 4.467 watts. So that takes account now of all the attenuators in series with one another in that system. So if I just come out a second there, so basically we're taking into account this 9 dBs now of attenuation, and then we've changed the spectrum analyzer to display power in watts instead of dBm, but of course you can change it back to dBm if you like. It's entirely up to you. You can do what you please, but that's just a rundown of how to attenuate the signals into a spectrum analyzer. So with that, I'll end the video here. I hope you've enjoyed the video and the demonstration that we've done with different attenuators, how to set up a spectrum analyzer to show the reading when taking into account attenuators. We've looked at faulty attenuators, Marconi, Narda attenuators, radial attenuators, every JFWs, I think they are, mini circuit attenuators. We looked at every attenuator, including variable attenuators, step attenuators, fixed attenuators. I've also got some pin diode attenuators as well, which I'd like to show in another video. But again, it gives you an idea of what you can do, and give you that confidence that if you want to do a measurement, you can do, and it's not rocket science at the end of the day. And you know, and just enjoy making measurements and doing repairs and configuring equipment and aligning equipment.